I forgot where I threw my boomerang. Oh, it's coming back to me now. Yeah. Oh, hello, and welcome. Today we're going to talk about surface areas of revolution. So what we're going to do is take a piece of a graph of a function and rotate it either about the x-axis or about the y-axis and calculate the surface area that's mapped out by that process. So let's first suppose that we take a little piece of arc and rotate it about the x-axis. I'm going to move myself over to the left side so you can actually see the little drawing on the right side. So here we just have a little piece of a function and we're rotating it about the x-axis. Now we're not, unlike chapter 6, considering the region under the curve. That region, if we rotated it about, would create a solid, so it would be filled in. All we're doing here is looking at the piece of curve itself, and when we rotate it about, you end up with just some kind of shell, right? It's kind of like a cylindrical shell, but in this case they're not cylinders. It's going to be some other kind of shape. So our goal is to find the surface area that's created. Now it turns out that the area of this surface is able to be calculated by the integral from a to b, so that's the start x value to the end x value of your interval, of 2 pi r ds. Now r in this case is the distance, so r is the distance if you're at some given x value. R is this distance from the axis of rotation up to the curve, right? So you can think about if this part of the curve rotates around, it's going to orbit around the x-axis with like a little circle. Okay, so look at this. So then if we think about the 2 pi r, that corresponds with the circumference. That corresponds with the distance that that little piece has to travel. Now the length of that little piece we can represent with ds. Remember, ds represents an infinitesimally small piece of the curve, and it's the length of that infinitesimally small piece of the curve. And if you remember back in 8.1, that section where we talked about arc lengths, you can either write ds in terms of x or dx, or you can write it in terms of y. So you can write ds equals the square root of 1 plus dy dx squared and then dx. Or you can write ds equals the square root of 1 plus dx dy squared and then dy. So it kind of depends. If you have y as a function of x, then you would use the first one. If you have x as a function of y, you can use the second one. If it's a function either way, so if it's like a one-to-one function where it's got an inverse, then it would be a function either way, and you could use either one you wanted to. You would have a choice. Now one thing is that you would need your function, so let's say we're taking y as a function of x, you would need your function to be greater than or equal to 0 on your interval. The reason for that is if the function falls below the x-axis or has negative values, then when you're doing these computations, you're going to end up with these negative surface areas, but that's not what our goal is here. We want the positive surface area, not like a net surface area of some sort. We also need f prime to be continuous on the interval from a to b. In other words, the curve has to be smooth. We can't have like corners or things like that. If we did have corners, we could just break up our interval into separate intervals, but we're not going to really look at that here. So if we take that integral from a to b of 2 pi r ds and replace r with what it is in the picture, the radius is really just the distance from the x-axis up to our graph, which is we can represent with y. Then we can replace r with y, and then the ds we can replace with the square root of 1 plus dy dx squared, and then we have our dx at the end. So that's one version of the surface area formula. So in example 1, we're going to use that, and I'll move myself over to there. Yes. Okay. Having too much fun with OBS Studio. All right. If you ever like to make videos like this, by the way, OBS Studio is great. It's free, open source, and pretty powerful. So I've been enjoying using it. and have some plans for some future little gimmicks and tricks. Okay, so example 1 says find the area of the surface generated by revolving the curve y equals the square root of x from x going from 3/4 to 15/4. I'm just going to draw a little picture of what's going on here. We're going to draw the square root function in the xy plane. And I'll draw the square root function. This goes out to 15/4. 15/4 is about 4. It's close to 4. I'll write 4 for our scale there. And then at 4, the y value is 2, right? Square root of 4 is 2. And then we have another y value of 1. I'll just put it there. Now we're only taking the part of the function that's from 3/4, which is just before 1, to 15/4, which is just before 4. So we're just taking that piece between 3/4 and 15/4. And we're rotating this about the x-axis. So I'll write the little rotation symbol about the x-axis. I'll draw a little shadow copy of that piece of the function on the other side. And then accompany that with some little rotation kind of marks at the start and the end of our interval. All right. And if we're if we're rotating about the x-axis like this, then the place where we're going to get these circles, these circle cross sections, are going to be perpendicular to that. So if we consider at a given x value, if we consider a radius going from the x-axis up to the curve, if we spin that little piece of the curve around the x-axis, it's going to travel a distance of that circumference of that circle that we just drew. So now this radius here is given by y, right? Y is that vertical distance of the radius. Now if we were spinning about the y-axis, well, then it'd be different. Then the radius would be x, right? It'd be x. It'd be a horizontal distance. It'd be x. Okay, just to label our function 2, I'm going to write y equals the square root of x. That's the function that we're looking at. Now to find the surface area, we can just write the general formula, which is going to be 2 pi times the radius r times ds. That's always a starting point for all these surface area kind of problems. 2 pi times the radius times a little infinitesimally small piece of the arc, which is what ds represents. And then we have, let's see, so we're going to replace the r with a y. So we can replace the r with a y, and that's because we're rotating about the x-axis. So when you rotate about the x-axis, your radius is y. If you rotate it about the y-axis, the radius is x, just like we mentioned a moment ago. And here we have a choice about what we want to use for ds. We could choose either of those two options that we were talking about before. Now since we've got y as a function of x, I'm going to go ahead and use the first one where we're going to write things with a dx at the end. So I'm going to write things in terms of x in just a moment. That moment has come. So here we're going to write ds equals the square root of 1 plus open paren dy dx squared dx. In other words, we're integrating, we're going to set up this integral with respect to x. WTR just means with respect to. Now in this case, we can write what dy dx is. So here we're going to replace the ds with the square root of 1 plus dy dx, which is 1 over 2 square root of x squared. That's the derivative of the square root of x. And then we have our dx at the end. So far so good. Now we can actually write the limits of integration too, but let's do that at the very next step when we're going to write everything in terms of x. Because right now we have a y in place of r, but since we're going to integrate with respect to x, we want everything in terms of x. But thankfully we have y is equal to the square root of x. That's what gives us those y values, is the square root of x. In fact, you could have gone right in and written the square root of x there if you wanted to. I'll simplify inside the radical. This 1 over 2 square root of x is going to be 1 over 4x. And let's go ahead and write our limits of integration now. Here we have x going from 3/4 to 15/4. Okay, so that's looking pretty good. That's the setup. From here we can continue on, and I'm going to do so because there's some interesting stuff going on. And how would we find the antiderivative here? Well, first we can pull out the 2 pi, get that out of the way. And the next thing we can do is, because we have a radical times a radical, we can multiply the insides of the radical together. So here we're going to have the square root of x times 1 plus 1 over 4x. Now we can distribute the x. So we have 2 pi times the integral from 3/4 to 15/4 of the square root of x plus 1/4 dx. And that's something that we can integrate. That one is x plus 1/4 to the half power, and we could do a little u substitution if we wanted to, or just do a mental u substitution, and we would get x plus 1/4 to the, let's see, 1/2 plus 1, that's 3/2. Divide by the 3/2, which is like multiplying by 2/3. So take that antiderivative from 3/4 to 15/4. And then we can plug in. So we have 2/3, 15/4 plus 1/4 to the 3/2 minus 2/3, 3/4 plus 1/4 to the 3/2. Here, if you look at 15/4 plus 1/4, that's 16/4, which is 4. And here, 3/4 plus 1/4 is 1. So this simplifies quite a bit. In fact, you could take the 2/3 and factor it out and write 4 pi over 3. And then you have 4 to the 2/3, that's the square root of 4. So the square root of 4 is 2, raised to the 3 is 8. Then you have minus, I took this 2/3 out already. So then we have 1 to the 3/2. I think I said 2/3 earlier, I meant 3/2. 1 to the 3/2 is just 1. So you get 7 times 4 pi is 28 pi over 3. Great, so that is the surface area of the square root of x from x equals 3/4 to x equals 15/4 rotated about the x-axis. Thanks for watching, and see you in the next video.